Let's get started. Super. Yeah, thanks very much for having me here, and thank you for attending the session. Also, actually, there will be now 2 consecutive talks. So I will here talk about a few use cases on quantum magnetometry, and I think then later on Q-control will focus down more on the navigation aspect where they did really strong work. So welcome to my talk. I'm René Reimann. I'm the director of the quantum sensing team here from the Technology Innovation Institute in Abu Dhabi. And I want to tell you about 3 use cases, and I also would like to introduce the core technology, this kind of magnetic field sensor, quantum magnetic field sensor to you, because I think it's less known than the other aspects of the quantum domain, namely computing aspects and communication aspects. Good. So let me start with a motivation, and this is a motivation we have heard several times. So this kind of big question: how do vehicles navigate, also vessels or ships? And we all know that the global navigation and satellite system is key to this for precise navigation. But it can fail, and not only fail, but it can kind of be hindered by jamming and spoofing, which is something which we see nowadays more and more, unfortunately. The ship, however, has a backup system. I mean, how a ship navigates is more complicated, but to break it down in a nutshell, it has a backup system, and this backup system would be a so-called inertial navigation system, which is based on gyroscopes and accelerometers and helps you then to calculate the position of your ship and to navigate. If you look closer into how these systems work, so at the core of these systems, there is, for instance, an accelerometer, and if you look at these accelerometers as depicted here, you can see that there are 2 key figures of merit. One is called the bias stability. It's, in the end, tells you how accurately is your sensor measuring the acceleration, here depicted in micro g. So g would be the acceleration of Earth, and the other one would be the scale factor stability. But to nail it down, it's about stability of the system. If you now take a standard accelerometer as you have it on a vessel, and this would have about a bias stability of 10 micro g, which means your measurement which you do is off by 10 micro g from the real acceleration. Now you want to calculate how precise is my position estimation. It's a very simple estimation. You can just say how much I'm off. I can calculate by half of this value bias times the time squared for which I navigate. And if you plug the numbers in, you find that after 1 hour of navigation, you're about 1 kilometer off. That's not too bad, but also not so good. Bad thing is that this scales quadratically with time, right? So if you navigate now for 4 hours, you're off by 16 kilometers and so on. So clearly, that's not a great solution. So this is now a cliffhanger, so I leave it there. And the idea is that these quantum magnetometers will now help you to make this better. And I come back to this, but now let me first introduce the technology to you. So there are currently 2 classes of sensors which are developed mainly in the industry. One is the so-called optically pumped magnetometer, and the other ones are nitrogen vacancy sensors in diamond, which are used for magnetic field sensing applications. And so to compare those, so that's an exercise which we did before we started working on this. We made this little table, and so you have these optically pumped magnetometers. They're based on hot atomic vapors. I'll tell you a bit more about this later. And these NV centers, which are solid-state systems. Now, the interesting question is, what can you use them for? The application there's a manifold of applications for the OPMs, for magnetic navigation exploration. 2 topics I touch on, then can characterize materials, also something I touch. And in the medical sectors, they are used, and they're overall drift-free, highly sensitive magnetometers. For the NV magnetometers, they are used or plan to be used in advanced navigation, exploration, and nanoscale material characterization, and they have an advantage over the OPMs. They have a very high dynamic range. You can measure huge fields if this is necessary sometimes. And they are vectorial, opposed to the OPM, which means they do not only measure the size of the magnetic field, but also where it points to, which is sometimes important. If you look in kind of technology readiness level, you find that the optically pumped magnetometers are much more technologically ready, and the NVMs are just coming right now. Then one important property is the sensitivity of these sensors. This tells you how small a field can you measure in a given time. And if you look at the best optically pumped magnetometers, they're crazily good, like femtotesla to attotesla. To give you a scale, in this room on Earth, you have a field on the scale of few tens of microtesla. So femtotesla would be more than 1 billion times smaller than these fields, which we have here in this room, which they can detect. And the NVs are not so strong there when it comes to detecting small fields. And then how large the fields can be, OPMs are perfect for Earth magnetic environments or also shielded environments in the medical sector. NVM's not limiting at all when it comes to how large the field can be. Okay, and how fast is also a question not too important here, and this I already said, scalar vectorial. That's kind of a little cheat table. If you have an application, you can look at this and then make your mind up which sensor might fit best to your application. Okay, so for the tech introduction, so now I focus on the optically pumped magnetometers, on the OPMs, and I just give you a little kind of 1 minute idea of how this works. So what you need for this is, on the hardware side, you need some optics, so you can see some little mirrors and little glass cubes sitting there. You need a laser which is coming in here, and the central element is sitting here. And in there, that's a glass cell, there are atoms, typically alkali atoms. And what's the idea now? The idea is that your laser talks to these atoms and makes them responsive to a magnetic field. You can think about a little arrow pointing in a direction. In this little arrow, we call it spin. This little arrow would now, if you put it into a magnetic field, start to rotate or precess around with a certain frequency. And the good part is that this frequency only depends on natural constants. That's kind of where this quantum aspect comes in, and the magnetic field. So it's a drift-free, highly accurate and precise sensor which you can build with this. And then in the end, you detect this kind of precession of the spins, this oscillation of the spins. You detect it optically. And that's about it, right? Conceptually, fairly simple. So how does this now help for this idea of navigating with a ship and using these optically pumped magnetometers or magnetic field sensors to make this better? This is now the use case number 1, magnetic navigation. Okay, so you know that there is the magnetic field of the Earth, and if you look at this, it looks about like this. It has a size of, in this case, about 10-ish microtesla, so it says here 60,000 femtotesla or so. And you can see that this field is, as a function of position, not changing too much. So if you're now sitting on the equator of Earth, you won't quite know, am I now sitting, I don't know, here, a little bit east, a little bit west. It's not quite clear just from looking at this field strength. You can use it, of course, for finding the north and the south. That's how a compass works, but it's not good enough to really tell you in which direction you're navigating. However, that's not the full story. On top of this field, of this total magnetic field, there sits a so-called anomaly field. And the anomaly field comes not from the kind of dipolar field which comes from the core of the Earth, but it comes from the crust of the Earth. So there are magnetic materials in the crust of the Earth, and they would make a tiny magnetic field which sits on top of the normal magnetic field. It's 1,000 times smaller. Okay, so it's very hard to detect. So now you understand, you see where this kind of magnetic field sensing with a very sensitive magnetometer comes in. And the good part is now that this field is spatially highly dependent. So it's very different if you're now here or you're off by a few kilometers. So it varies a lot, and what you can then do is you can measure this field and make a map of it. And then as you navigate with your vessel or with your plane or your car, you can then compare the measurement as you do it, as you navigate, with the map which you have recorded. So you do feature mapping in the end, and with this you can find out where you are. And so in putting this now into kind of a technological product chain, if you want so, you would need the following for good GNSS-less navigation. And so you need, of course, your accurate and precise magnetometer. Then you need the anomaly map in the area where you want to navigate. You can, of course, also measure this yourself if it doesn't exist yet. It's actually an issue here in the UAE. Turns out the UAE doesn't have a lot of maps, and it's also pretty flat, so there are not a lot of variations. So it's very hard to do this here, but it's a nice challenge, of course, also on the other hand. And the very important part, and this where Q control is also very strong, is the algorithmic part, where you, of course, need to do map propagation, so the maps are measured at certain heights, and you might be at a different height, so you have to calculate this. Then you need to do denoising, and one big part is also sensor fusion, because this whole system will not work as standalone, but it will, of course, fuse it together with the knowledge of your other systems, for instance, your inertial navigation system. Good, so this was now our first use case discussion. So what we are focusing on at TII is we right now build this hardware. We also work on the software and algorithmic part. But as my team is the hardware team, I focus on this. So that's what our sensor looks like. Right now for scale, there's a little AA battery next to it. So there's the box is a control unit, the aluminum box in the background, and the sensor head is really the kind of black thing with a transparent lid for looking into it on top. Then I told you that there is this kind of oscillation of the spins, which really tells you what the magnetic field value is. So this would be one of these raw data, which you then get out of the sensor. And then one important figure of merit is the sensitivity. So how small can the field be your sensor measures, and that's really important for these applications which we're discussing here. And there you find sensitivities on the level of a picotesla per squared hertz, which means you can sense a picotesla within about 1 second, which again is more than 1 million times smaller than the field of the Earth, the normal Earth magnetic field. And so in terms of swap of kind of what the thing right now looks like, so still a bit bulky, 8 liters, but the sensor head is fairly integrated, weighs about 4 kilos, the whole thing, and the power consumption is average 22 watts and peak 50 watts. These specs are all right. They are not super impressive, but what is impressive, so what we are proud of is that we were able to do this within 6 months. And we just started very recently doing this, and of course we pushed this because we have to get this going as quickly as possible. Okay, so this was the first use case. Now there are 2 more use cases, which I use my last 10 minutes for. And those are now from a different sector. There we have an industry collaboration with the Abu Dhabi National Oil Company, ADNOC. And we started working on these 2 projects beginning of this year. So number 1 would be battery inspection and prediction. We give you a motivation for this. So we look at lithium-ion batteries, and of course lithium-ion batteries power a large part of our infrastructure, right? Also in kind of all sectors. If you look at the civil sector, defense sector, plays a big role more and more. Also of course, in the maritime domain, there are also ideas to have ships powered with lithium-ion batteries, or also submarines. So the overall idea is here, if you were able to know the state of charge of a battery, so how much is charged, and from this, eventually, if you have a lot of data on also the remaining useful lifetime, you could, of course, predict a lot of things, right? You could reduce downtime and cost, you could enhance the safety of the system, and also enhance the battery lifetime. So it goes under predictive maintenance and system optimization, if you were able to do that. So what's the approach which we are taking here? So again, we had this before, right? Somebody said this here, I think in the last session, that quantum is never played alone. You always kind of fuse it together with a lot of other parts which matter equally. So for developing a kind of a meaningful tech stack, what we do is we do kind of classical state-of-the-art battery measurements and parameter extraction. For this, you have to kind of dissect your battery. So we do this with our material science team. So it's a project where many teams from TRI come together. We do classical battery measurements. This is what you see up here on the left, where it's called cycling. So you discharge the battery, and with this you learn a lot about what your battery is built from. It's interesting that this is you cannot simply get this from the market, because how it works is that the people or the companies who build batteries, they won't tell you how the battery is exactly built, so you have to kind of acquire this knowledge yourself if you want, because of course they guard this knowledge and don't want to put it out easily. So that's the classical part. Then there's another idea. The other idea is these measurements, of course, are invasive, and you also potentially destroy the battery as you do this, but it's important to learn something about the battery. The second part would then be the quantum measurement part, which is non-evasive, so you don't distract or kill the battery as you do this, and the idea is as a current flows through the battery, there's a magnetic field created. With a sensitive magnetometer, you can measure this magnetic field, learn something about the current, and also learn something about the state of health and the state of charge of the battery. And then you, of course, again, machine learning AI, you have to mix this all up into a clever machine learning model, and this then would enable you to build a highly accurate digital twin, into which you would still also feed data to make accurate predictions. All right, and so this is kind of just a snapshot. So this is the machine learning model we are doing there, and what you can see is we kind of run, that's a simulation now, it's not yet on any real data. But we run as a function of time the cycling, so we kind of discharge the battery in the model, and then we feed this into the machine learning model and ask it to predict the voltage state, and you can see that the prediction pretty nicely follows what you would get out there. It's kind of the first step, right? There's more to come on this. Good. Then final use case, also this, funnily, we had touched up on before. It's about carbon capture and storage. The idea is to hit our climate and sustainability targets, we are starting to put carbon dioxide into the ground to store it there, because it's not good if it's in the atmosphere because of the greenhouse effect. And so what you do there is you capture your carbon dioxide, then you compress it, you make it hypercritical, and then you pump it into the ground, into large depths, like below 1 kilometer. As you do this, there's a bit an issue. The issue is that you don't quite know if the stuff stays down there. You pump it down, right, but there might be a little bit of crack, and it might eventually come out again, and it's very hard to detect, right? And so there are classical state-of-the-art methods on how to look into this, and these methods are called CSEM, standing for Controlled Source Electromagnetics. How does it work? What you do is you put electrodes into the ground, and you send an electromagnetic field there, and then you also have receivers, electrical and magnetic field recorders, and they would pick up the response of whatever you have in the ground. And so from a physics perspective, the idea is literally, let's say you had before salt water in there because you had an oil field, and you kind of washed this out with salt water. Has a certain conductivity, electrical conductivity. Now displace the salt water with CO2, the electrical conductivity changes, therefore the field response, or the electromagnetic field response of your material would also change. That's what you want to detect. Sounds easy, it's extremely tricky, right? There's a signal to noise plays a big role, and so what is our target here? Our target here is to understand this process better and to see if one can bring in quantum magnetometers to make better measurements on the magnetic field sensing side, and to predict better what's happening to your CO2 underground as you pump it in there. And so how we do this we do in a kind of well-controlled lab approach to get a good understanding of the underlying mechanistic processes. And so here you can see a little picture of we call it the CCS, carbon capture and storage rock sample characterizations setup, which we have built over the past 9 months. And what you see, there's of course kind of measurement electronics, some lock-in amplifiers, and also in the middle that's a magnetic shield. You want this again to have really well-controlled laboratory environments, and then you would have your rock samples and eventually pressurize them highly, try to mimic the conditions as you have them underground, and then really run currents and magnetic fields through it and see which kind of responses you get and how you can extrapolate this and eventually to roll it out in the field. So these are first measurements there. So we took a rock sample and put it into this machine, and then you would kind of scan it through. That's the x-axis, the position is scanned through. You can see as the rock sample comes in, the field changes. Also looking at the values which we measure there. So these are picotesla, again on the scale of 1,000,000 times smaller than the Earth's magnetic field. So to do these measurements accurately, you indeed have to go into this shielded environment. And you can also see that the measurement is very nicely reproducible. Because the value, what we do is also we rotate the stone angle to really scan through the full stone. So the values at 0 degrees and at 360 degrees, they are the same, right? Which is a good measure of reproducibility. All right, that's it. These have been the 3 use cases. Thanks a lot for your attention. And so a lot of people were involved in this. We also cooperate with the ADNOC team on this matter. Thanks a lot.